We are going to be looking at how to calculate the displacement due to the movement of the foundation. This figure here is to illustrate what we are going to be talking about. Assuming we have such a structure being supported by a rigid support at point A, if our structure undergoes a horizontal displacement given by magnitude delta XA to the left hand side, and then it undergoes a vertical displacement given by delta YA, that is a sinkage, and then we have a rotation given by theta A, we automatically know that these displacements here would induce point B and C to also undergo a displacement of some magnitude. So our interest is to find out how we are supposed to calculate these displacements. So first of all, let's try to look at the steps that we take in these calculations. The first step is we have to add a unit force at a point whose displacement is required. Then we calculate the reaction forces due to the action of the unit force. And then lastly, we have got to calculate the displacement from the equation delta is equal to negative Fr times the displacement at the support. Now let's take on the illustration above so as we try to see how the above steps are put into calculations. From the above illustration, let's assume that they want us to find the horizontal displacement at a point B. From the steps that we said above, we said that the first thing that we need to do is to add a unit force at the point whose displacement is required. So for this case, since they want the horizontal displacement, that means we've got to add a unit force that is horizontal at a point B. Let's assume that it is in the horizontal direction acting towards the right hand side. So we come and add on our unit force Fp is equal to 1. So after adding this, the next step was that we are supposed to find the reactions due to the action of the unit force. So since we only have the horizontal force that is acting on the system, that means that we are supposed to have a horizontal force that counteracts it in the opposite direction. So here we shall be having a force of magnitude 1. Yeah. Then from this we see that this system of forces form up a clockwise. They form up a couple acting in the clockwise direction, that is of a magnitude B. That is a force we take the force which is 1 times the distance between them, which is a B. So that means that they need a moment that is acting in a opposite direction to counteract them. So our moment would be in the anticlockwise direction, with a magnitude of B. So let's assume the moment is given by M. This is MB is equal to B, and then this force here, let me label it F in the X direction acting at a point A. So after we've done this, we say that the next step is now to calculate for our displacement. So our displacement delta XB will be equal to negative of the summation of the reaction forces times the displacements delta. So here in this case our displacement would be equal to our reactions. So we have a negative, then for the sake of our reactions we only have two. We have the MB, and then we have got the FXA. So that means that we are going to be having our force that is we are having MB times its displacement, let me call it theta A, plus FXA, then times the displacement which is given by delta XA, like that. So this one here would be equal to negative into our MB is equal to B, and then I want us to take note of the displacement. When you look at the arrow of the force, the arrow of the resultant force due to the action of a unit force, and then the actual displacement that was due to the movement of the foundation, these two are in opposite directions. So whenever the the resultant force and the initial displacement are in opposite directions, the displacement is given a negative sign. And then if at all they are in the positive directions, they take on a positive sign. So here it will be now multiplied by a negative theta a, then plus. Now let's try to look at the force Fxa, Fxa, and then the displacement that it caused there in the direction. All of them act towards the left hand side. So that means that here we shall be having our force as 1 times our displacement was delta xa. So this gives us a displacement that is equivalent to this, and this becomes a positive. We shall be having a b theta a, then minus this should be delta x a. So the displacement at point B on the system due to the movement of the foundation at A would be equivalent to this value here that we've calculated. Likewise, if let's say we assume that the question had required us to find the vertical displacement, let's say at point B or at point C, the same steps are required, but now our unit force would be placed in the vertical direction. You can try that out and see the answer that you come up with. Here comes our second example. It says, find the horizontal displacement at point C. So this is our point C, and we are going to be following the same steps as we had said. So with this system here, we shall have to apply a horizontal unit force at point C. That is of this nature. This is Fp is equal to 1. And then we know that at a hinge, that is at point A, we have two reaction forces, one of them in the horizontal, one in the vertical. So therefore, automatically the one in the horizontal must act opposite to the one acting at point C. So this also would be equal to a 1. Let me call it force XA. This would be equal to a 1. Then now, like these two forces, the Fp and then the XA1 will be forming a couple that tends to make the system to turn in the clockwise direction. Therefore, I can use this idea to directly deduce the magnitude of the forces that are acting at point A and point B, since the dimensions are the same. Here we have L and then L. So that implies that we must also be having a couple to counteract the same forces. Therefore, here we shall be having a force that would be a couple that causes the system to be turning in the anti-clockwise direction, that would be upwards. So we shall be having this one and then this one here acting opposite to that one above. So their magnitude must be equal to a 1, and this one here must also be equal to 1. So after writing down our forces, the next is to do the calculations. Like we say that our formula of calculation is that the displacement that is at C, let me call it delta xc, since it is in the x direction, that is the horizontal, is supposed to be equal to negative of the reaction forces times the displacement. So this would be equal to negative into, so our reactions, if let's say we begin with the x direction, we see that in the x we have a force that is of magnitude 1, but the displacement is opposite to the direction of the force. So therefore, we must multiply it by negative b. Then next we come to the force in the vertical direction. We see that the force is acting downwards and then the displacement is also downwards. So therefore it will be an addition sign. So plus, that would be 1 times A. This gives us an answer that is equivalent to that will be B minus A. So I want you to try to calculate the vertical displacement at a point C. And I believe the answer to that, you must find an answer that is equivalent to, it must be equivalent to positive A. as a vertical displacement at point C. Try to calculate it out, please. With the next example, they want us to find the horizontal, the vertical displacement, and the rotation at point D. That is at this point here. So you can try it on your own before you look at the calculations that I'm going to give. Okay, let me hope that you've tried on your own. Then let's try to work it out together now. We know that if they want the horizontal displacement at a point D, we've got to add a unit force in the horizontal direction. Let's say it's given by Fp is equal to 1. Then if this is Fp is equal to 1, we shall have a reaction in the horizontal that will be equivalent to, let me call it Fax would be equal to 1. Then the vertical displacement would be equal to 0 since we have no vertical force. Then we shall be having a moment also since it is a rigid support. And then our moment, when we take the moment at point A, we shall discover that the moment MA would be equal to A. So therefore we move on and calculate our displacement. So our displacement delta x, that is displacement in the x direction, would be equal to negative summation of Fr times the displacement. This would be equal to negative, open the bracket. We first begin by looking at the forces in the x direction. We see that the force in the x direction is acting towards the right hand side, yet the displacement is acting, yet the displacement that we were given was towards the left. So therefore we shall be having a negative sign here. So this would be negative 1 times our displacement, that is delta x. Then when we consider the moment MA and then the given moment in the system are also in opposite direction, so therefore we also add a negative sign. Then the moment was given by A times the displacement delta phi. So this gives us an answer that is equivalent to delta x plus A delta phi. That is for the sake of displacement in the horizontal direction at point D. Next, we are going to look at the displacement in the vertical direction. Okay, so for this one here, we said, what do? We've got to add a unit force at the point where displacement is required, that is point D. So we add a unit force Fp is equal to 1 in the vertical direction since we are finding the vertical displacement. Then if this is Fp is equal to 1, that means we shall be having a vertical reaction also, but in the opposite direction at the rigid support of magnitude Fya would be equal to 1. Then we come and take our moments at point A, and then we discover that we shall be having a moment that is equivalent to 3A. So we've like for the sake of the x, we won't have the x since there is no force in the x direction. So after doing that, we come and find our displacement delta y. Our delta y would be equivalent to negative summation of the reaction forces times the displacement delta. So this would be equal to negative. So here our moment is 3A, then times we look at if we go back to the original question, we see that it is in the same direction as the angular rotation, so it takes on a positive. So that is times delta phi. Then if now we look at if you look at the vertical displacement and the vertical force of reaction, we see that they are opposite. The displacement was downwards, but then the reaction is upwards. So we add a negative. The force is 1, then times our displacement was given by delta y. So therefore, we would have our final answer for the displacement as delta y minus 3a times delta phi. This is our answer. And lastly, let us look at the calculation for the rotation at point D. So unlike the displacement where we had to use a unit force, for the sake of finding rotation at any point, we are supposed to apply a unit moment because rotations are as a result of moments, while displacements are usually as results of what? Of forces. So therefore, we come and add a unit force that is at point D. Let's give it a clockwise anti-clockwise direction. Let's say it's given by mk is equal to md is equal to a 1, and then if this is acting anti-clockwise, that means that the reaction at the rigid support would be acting in a clockwise direction. That will be ma would be equal to 1. Then we come and calculate our displacement as delta theta would be equal to negative summation fr times our displacement delta. So this would be equal to negative into bracket our resultant force or resultant moment is given by a 1, but let's check upwards and see whether they're in the same direction. We see that it's opposite to the direction of the displacement at the foundation, so therefore it takes on a negative sign. So this would be negative 1 times delta phi. Thus we get our displacement as delta phi. So with this, I guess the calculation of displacements at a foundation have been fully covered. Thank you so